Hi there everybody, and welcome to the third lecture in our webinar series on reducing doubt in measurement and test, hosted by the Engineering Integrity Society. The EIS is a long and established charitable society focusing on areas of testing, measurement, durability, fatigue, sound and vibration. It's a unique forum for engineers to exchange ideas and experience. And I've been an active member in the foundation since its foundation in 1985. It's an excellent forum for discussion, networking and learning, like these webinars, on all aspects of engineering, test and development. It's supported worldwide by a number of senior sponsors, and it consists of quite a few groups. We have here the simulation test, it's a number of groups, sponsor companies and a wide diverse group of engineering experts. As you can see, there's quite a few. Every year we host numerous events such as webinars like today, and larger events such as Silverstone Instrumentation Analysis and Testing Exhibition. That works so far. So far we've had two excellent presentations by Damien Harty on how variable and uncertain is the development world for rally cars, and then by Miles Dadson on the uncertainty of measurements in the calibration lab. We now move on to our third. This is by Peter Bailey, who will give us a presentation on uncertainty collection, a materials testing case study on variability outside the specimen. Dr. Peter Bailey is a principal application specialist at Instron Dynamics. That's a fatigue and analysis testing machine manufacturer and work in that field. Peter is an experimental materials scientist working on advanced mechanical testing and characterization techniques. He specializes in all types of material characterization as well as small component testing. Peter's background, I've known him for quite a few years, includes a wealth of experience in research into polymers and composites and a variety of production and quality control methods for thermoplastics and thermosets. Somewhat fundamental in our topic, I think, of reducing doubt in analysis and testing. His more recent work is on fracture mechanics and fatigue of materials. So over to Peter for his presentation. Thanks very much.
Thank you, Dave. That's brilliant. Kind introduction there. What I will just do is start by sharing my presentation so that you can all see it. There we go. So yes, as Dave says, I'm Pete Bailey. I work for Instron, based in High Wycombe here in the UK, in particular on Instron Dynamic Systems. So that's our servo hydraulic and electrodynamic systems. So my role is to be the center point for all knowledge on all things fatigue and fracture and durability testing within Instron. So what I'm going to talk about a little bit about today is through the lens of materials testing, some of the things that create uncertainty and will interfere with your test. And some of both at a generic level and with some specific cases and examples, and then indicate at the end a little bit about, well, where that can take you. So the wider series of webinars, you've started, as Dave said, with some sort of some fundamentals, and after me over the forthcoming week or so, there are a number of others working up to bigger and bigger and more complex things. So hopefully it sits in the middle and might be useful as a stepping stone, or indeed, if you're in materials testing, of itself. So giving you an overview of how I'm going to go through things there this afternoon, starting with kind of where the take on mechanical testing and where we're starting from, then a little bit about taking measurements, then what happens as we get from simple measurements into running a complete test, specimen interference. So, well, there's quite a topic in itself, but I'll explain that in a while. Analyzing the data is can be a very significant effect, or can have very significant effects on the output of whatever you define as your test. Last of all, uncertainty budgeting. Now this I don't claim as an area of great strength for me, but I'm going to touch on it and sort of talk a little bit about just how far you can go if you choose to. So let's start with mechanical testing. What's the world that we're talking about here? So as most of you will know, I hope, Instron have made mechanical testing machines for a very long time. And for a large part of that, we've also done ones for fatigue and fracture testing, so dynamic loading. Most of the work is on coupons of material, or sometimes, more and more of recent years, small assemblies and widgets. I say widgets, that can be tools, that can be medical devices, all sorts of things where we're not just looking at the material properties. It's a small thing that we're looking to analyze its mechanical behavior between force and displacement and strain. So materials testing in particular is really quite a well-established field. And there's certainly well over a century of work with increasingly sophisticated machines and measurement techniques. As an industry, the discussion of uncertainty on measurements is something that's been growing over, well, I suppose, over longer than my career, where it's grown in importance over the last 30 years. But there's really been an increased interest again in perhaps the last 10 years, during the time I've been with Instron. The downside of that is people ask us as materials testing professionals, us as Instron, as equipment manufacturers, the whole business about, well, what's the uncertainty on that measurement? And at times that's quite reasonable. So how certain are you? What's the possible error on the tensile strength of this steel? And it's not too bad. But the further you go along the path of durability, which is very much the interest of this association, the VIS, we're interested in durability and equally dynamic performance, things like NVH. Quantifying the uncertainty becomes harder and harder. Doubly so because there's variability between one specimen and the next, or one test piece and the next. Does that mean it's a completely futile exercise? No, it doesn't. But there are lots of different things, and often what we need to do is work to eliminate or minimize each source. That can often be much more important than summing it up. So as I said, my particular interests are in fatigue and fracture mechanics, and so a lot of the things I'll talk about today are seen with that perspective, or discussed with that perspective. Now here we're starting to identify more complex characteristics in a material, and we're very sensitive to physical variations between one material and another, between one batch of material and another, between one specimen and the next, as I say. And that's a fantastic thing with that sensitivity. In terms of that's the point, the object of the exercise, and that's the value of our area of study. It finds differences between materials which are critical to the structural integrity of a let's say an aircraft, which you simply wouldn't identify by doing a simple tensile test. The trouble is that when we get so sensitive, if we don't really handle other sources of uncertainty, then our test might stop being comparable between one test program and the next is the worst possible thing, but equally between one lab and laboratory and another. Not a situation you want. And today, in today's world, we expect to be able to be more and more reproducible between one laboratory and another, one operator and another. So let's start with basics then. I'm not going to dwell too much on this, since I know that I think Miles would have spoken a lot about a lot of good stuff in terms of just calibration. But step one, we've got to understand our basic tools, whether it's a load cell, a force measurement device, or whether it's a ruler, a set of calipers, simply measuring dimensions. We need to understand about that single measurement. You can take time out of the equation for a moment, take other parallel measurements out of the equations, just say one measurement. Fundamentals. Is it well calibrated? Are the millimeter markings actually a millimeter apart? Are they all a millimeter apart consistently? Or are they all slightly over length? Or is one end of my measurement device slightly short measurements, the other end slightly long? How consistent is it? Equally, if I pick up my specimen, probably I'm not actually at my desk, so I don't have one to hand. But if I measure my phone, measure how wide is my phone, and I take a measurement with a set of calipers across here, and then let's say Dave, I pass him the calipers and the phone and ask him to do the same measurement. Is he going to get the same measurement? I mean, realistically, we know that there'll be a tiny difference, but is it a tiny difference in the resolution of the device, or is there some variability that's added by a different set of hands, a different operator? Last of all, does the environment affect the reading? And sticking with the idea of dimensional measurement just for a moment, some of you may be aware that there are standards and agreements on that which are very prescriptive. So standard dimensional measurement conditions are 20 degrees C plus or minus 1. And this becomes important because the temperature of your workpiece will cause thermal expansion or contraction, and equally, if we're using mechanical tools, then your ruler will get longer and shorter if you make a significant change in temperature. So the environment can affect the reading. All of these things can add up, and they can be some of them can be random, and some of them can be systematic errors. So a device which is calibrated as with a 1% error all the way up that's a systematic error. A random error might be how well aligned I get my calipers on my workpiece, and there'll be some degree of variability on that, which is quite random. So picking up on this I mentioned the calibration issue. Let's talk about that for a minute then. So practically, we have verification procedures. We calibrate our device, whatever it is, and then we should, as good practice, verify that when we've got it in place and we come to use it, or before we use it, in fact. And that means that we can systematically declare an uncertainty on just that one measurement. Now, it might be, as I touched on just now, it might be proportional with the scale of the reading. This is quite common with electronic transducers, certainly within our business, where a lot of them are strain gauge based. So the error is declared as, for example, arbitrary figure 0.1% of the reading. So the absolute error will increase with the size of the reading. Or it might be absolute. It might be effectively the noise. It might be so good that it's effectively the noise level. And then it's absolute, and it stays the same whether you're trying to read 0 or whether you're trying to read nearly the full scale of the device, the full length and full span of your device. Now, the reality is that whatever happens, there will be a noise floor for it, certainly any electronic device. If you're talking about going back to that basic idea of optical measurement of length, you've got resolution, whether it's the ability of a human to define, to resolve, or whether you go into microscope optics and you get down to wavelengths of light. There's a noise floor everywhere. If we see that, and I've put up the calibration diagram, a classification diagram from ASTM E83. Now this is about extensometers. So it's about measuring strain or extension, depending. And I'm sorry, I haven't actually colorized this, which would make it clearer. But you see that they give a classification where it's a proportional error. So as the actual strain applied on the x-axis goes up, then the permitted error for a given classification also starts to window up because it's proportional. However, at the bottom end, towards the, hopefully you can see my cursor, but towards the left-hand side of the graph, you have this funnel, as it were. So below a certain reading, you say, actually, below this point, it doesn't make sense to try and get smaller and keep the same proportion of a vanishingly small measurement. It becomes impossible. So we have this idea of the main operating range, and then you have to adapt for the very, very tiniest measurements. And this drives me to say, this prompts me to say, when you're doing measurements, please use a transducer with a sensible range. If you're going to have a specimen where you're going to apply a force of, let's say, 500 newtons, and that's the biggest force you're going to apply, please don't do this using a load cell which is rated for 100 kilonewtons, because you are way down, and while it will give you a measurement, and in fact, it, blowing our own trumpet here as Instron, we can sometimes control quite well, even despite a lot of noise on the signal. That doesn't mean it's a good idea or a good test. So you're looking to be using a reasonable mid-range of your transducer, not right stretching it to its absolute capacity, not right down near 0. You will get poor data, relatively speaking, poor data out of that. And the proportional uncertainty becomes much, much bigger. Now, so this is all very good about just sort of straightforward calibration and verification. However, when we start talking about fatigue tests especially, they become long and they become slow. And calibration or verification conditions are realistically minutes or maybe an hour or so. We are often doing tests where a fatigue test will run for many hours, if not many days. And there are things that can creep in there where you can get drift happening in the transducer due to environmental changes, especially. Now, this is most significant where the things like the temperature changes. And this is why, once again, mechanical testing laboratories should be reasonably temperature controlled. Because a few degrees difference can be enough to shift the 0 point on your measurement, or it can shift the overall full-scale reading. So once again, for the people at the back, use a transducer with a sensible range. Let me give you a common fatigue testing example on this. That strain gauge devices, as I say, drift very slightly with room temperature. And historically, you talk to people who've been in this business a long time and have tried to do very precise measurements, and they'll all have examples where they do a strain controlled test, and the controlled channel will look perfect because the controller does its job and relies on the feedback. The trouble is that feedback is drifting slightly up and down between day and night. So they'll see the dependent channel, the force peaks for each cycle, for example, will drift up slightly during the day and drift down slightly overnight. There are always ways and means to deal with these things, but it's a common thing historically. So addressing that environment thing, well, you think, okay, well, specimen environment, if we've done everything right, then there should be no effect on the transducers. And it's usually, for a majority of tests, it's constant during the test. Perhaps as a poor choice, or I couldn't decide whether I like this or whether I dislike this, the image on the right-hand side here is actually a TMF test. That's a thermomechanical fatigue test, in which the specimen temperature cycles up and down during the test, as well as the mechanical strain. So there's an illustration there of a deliberately non-constant environment for the specimen. However, whether it's constant or otherwise, the environmental control can affect your reading. So that specimen environment can impinge on your reading. Now, it could be affecting the transducer temperature, like I said. It could affect the transducer coupling to the specimen. This one's one where we have to work hard, both we as manufacturers and operators in terms of making careful test setup, getting good coupling to the specimen. That environment could be less constant than we think. Let's say we're doing this inside a temperature chamber or furnace, and we think we've got 500 degrees plus or minus 2. If things aren't right, then we could have plus or minus 5 degrees. Or we might have only 1 degree variation, but it's offset by 10 degrees. All of these things start to shift our test results. But I'll come back to that in a few minutes. So we're starting to talk about test variability. And let's think about test variability outside the specimen or outside the material itself. So as I've said, if we've got things set up appropriately and we've got a good system, those basic uncertainties on things like force and strain, we can get them small. However, when we talk about practical engineering measurement and then simulating loading, which is effectively what fatigue testing is, it's as much about applying the relevant stimulus as about analyzing or measuring the response. So we need to ask that question of, are we actually loading our test piece as we intend? So let's first talk about the literal interpretation of that. The control fidelity? Are we hitting the targets? So in cyclic loading, this is really important to control, or at least record very accurately. And that's because, and apologies if I'm sort of teaching grandmother to suck eggs, teaching people things they already know very well, but damage accumulation depends strongly on amplitude, on the reversal between peaks and troughs, but also on history. So something as Instron we work hard to help people with, and something I preach rather a lot about, so apologies, slight hobby horse here, tuning and getting your system control accurate. If you don't do that well, then when you start your test, you might have one of the two scenarios here. So on the left-hand side, we start and we are not getting anything near the target that we want, and we gently envelope up. Now, there's a good history of doing that on purpose and ramping up over the first 10 or 100 cycles. Great, if that's what you intend. but do it intentionally and do it the same every time. Arguably worse, when we talk about those loading history effects, is if you've ended up a bit aggressive and you actually go over what you meant to, and you overshoot your target on the first few cycles. So with fatigue, that can have, particularly if you're doing aggressive loading just intentionally, if you overshoot further, it can really affect the fatigue life of the specimen. It can affect the work hardening. So when you talk about control, you want to know, are you getting to the target every time? And the thing I would emphasize here is that to a large, unless you can do very sophisticated analyses and infer things from this. That's not something I've ever worked on, and it's not within Instron's business. But some of the other members of EIS do work on this very much, and that's inferring from different amplitudes what damage you accumulate and how that translates. But let's be clear: the test control uncertainty it's not easy to translate that straight to an uncertainty in the result. So I always say, let's get it really accurate to start with. So the other thing is specimen loading. Let's say we're getting the control, great, and I've put systematic variability with some sarcasm here, because is that almost nonsense? Well, maybe. So there are things that happen with the mechanical aspects of the test setup. So let's say we're doing an axial loaded test, and so it should be purely uniaxial. But is it? And this is perhaps something some of you have encountered and talked about, and is the idea of gripping and getting accurate alignment. Now, if you clamp your specimen, clamp your test piece, and it's nicely aligned, everything's good. If you clamp it and one end has ended up offset or twisted, then you're now going to introduce some bending into your test piece. Now, what that means then is that one side, as you bend a specimen, obviously one side is pulled into tension, the other pushed into compression. So now the surface ligaments aren't going to be seeing the same as the average strain that you're intending to put on. Now, if it's something all very ductile and a great big specimen doing just a very basic tensile test, it probably won't make any measurable difference. Probably, mind you. However, it's been shown for many, many years that you can measurably influence the tensile strength just in a static test. If you have a very brittle, stiff material, something like a heavily fibre-reinforced composite. And similarly, if you're looking at fatigue testing or cyclic loading, then what this will do is, if you have a higher tensile stress on one side or at one point, then you will accelerate the crack initiation. And if you accelerate crack initiation, then you're going to take something at least off of the total fatigue line. Let's just briefly look at an example of this. Let's talk about this. There are techniques by which you can set up and measure this by instrumenting a specimen. People don't usually do this with each individual specimen. You do effectively a type verification, at least for the system, ideally each time you run each new batch of testing. So this is a polar plot of bending strain on the two axes. So left and right across the machine, out and front and back. Now, this is bending strain as percent of the average applied strain. Now, historically, if we look back in history and at some of our own designs, many other designs back in the mists of time, older mechanical clamp designs would very often allow you to have up to 10% what you might describe as parasitic strain, and 10% bending strain in addition to what you're trying to apply. Now that's quite significant. And for certain types of tensile testing, it's still permitted. But you'd get scatter everywhere within that outer dark red circle. In modern times, in fact, for a good 20 years and more, it's been mandated in various fatigue test standards that you must stay below 5%. And that was to some extent a somewhat arbitrary, challenging but achievable limit. Was where the origin of that 5% came from. Now, this data in particular I'm presenting here is showing this is some work we did. Once again, look! Here's some nice data. So apologies for the slight commercial bias there. There are other people who've done similar stuff. You'd get a really good grip design, and you can get your scatter really, really tight. So this is something like 38 different repeat measurements, and you can see that's really, really repeatable. And that's where, in modern times, we should all be trying to get to, because we're getting right down to the limits of what's physically available, and we're not introducing significant scatter to our results just by inadequate clamp design. I would mention, though, there that I've underlined plus the specimen tolerances, because best designed grip and clamping system in the world, if you don't machine your specimens very, very, very carefully, then you're also introducing a variation. So pursuing that thought, good and poor geometries. Standard geometries come mostly out of history. And they should be giving good effective clamping, so it's not going to slip in the gripping device, but also even strain distribution in the analysis volume, if you will, the gauge length. Most of them are good, but they've largely come out of things a long way back in time, and many were empirically based. Doesn't make them bad, but it's interesting, some of the work that's been going on in recent years where people start applying finite element analysis to kind of redesign and optimize their specimen geometries. Equally, there's some great work out there. I've been speaking to some folks from Ghent University in the Netherlands recently, looking at using image correlation to actually analyze and see what's happening during the test, and actually correlating, well, are we getting the strain distribution in our specimen that we think we should be? And much of it is good, but it reveals some interesting things if you follow that line of discussion and reading. Occasionally, however, you will find some standard specimens which are still there and lurking, and they compromise quite severely. My pet hate on this is parallel-sided, straight-sided composite test specimens. And these come out of the days when really you couldn't get a very good machining unless you used a diamond saw, and obviously you can't make a wasted specimen using a circular saw. That doesn't work. The outcome of this is that there is no good reason for them to break anywhere other than at the clamping point. You can see, just using thermal imaging, we can visualize very clearly how much extra heat is being generated, indicating there's a lot more aggressive loading just at the point where these specimens are clamped. So if it fails anywhere other than at the grip, there must have been a really big defect somewhere in the gauge section. As I say, a pet hate for me, but you will also find there are some other ones out there which are still in use and aren't great. Once again, carrying on with the careful preparation idea, we do need to be sure that the material is in the state you think it is. And this is tiptoeing into the area of, well, actually it is the material, but you should be thinking about it. So, as I've said before, we're very sensitive with fatigue and fracture to defects in the material and to residual stresses. So when you've got your specimen, or when you're preparing your specimen or asking your machine shop to do so, let's think about three things just to try and eliminate them. Was the machining process gentle? Now, if you do a deep cut, then you start putting a lot of shear into the surface layer of material. If you are not careful, it can go much deeper than your finishing. The early cuts could actually affect a deeper layer of material than even your finishing cuts and polishing could take away. And this stuff will change your crack initiation every day of the week, and therefore it affects your test results. On a similar topic, I mentioned final cut and polishing. You look at international standards on fatigue testing, they mention about certain levels of surface finish on the specimen. So we do need to get down below a certain effect. Unless, caveat on this, if you are going to do a test on a specimen which is actually, you're interested in the surface finish and you want it to be representative of some part. And there we're starting to diverge from materials testing, and we're starting to understand a little bit more about simulating the real parts. So, but make sure it's not having an inappropriate effect. Last of all, and this one is sometimes a bone of contention, is knowing whether your specimen has been overloaded before you get to the test. So don't bump it. Looking at the time, I do need to move along a little bit and talk about, so we'll move on to analysis. And what do we do? We've done our measurements, we've broken our specimen, we've got our data. So now let's do some analysis on this. And there are a lot of things in materials testing and engineering as a whole where there are concepts of slope and initiation or onset points, and they're really central to some of our theories. And the reality is that they're practically derived from graphical data. And that stuff is easy for a human, or certainly a trained human. The trouble is that humans aren't terribly consistent. Certainly not one to another, and not always the same human on 2 different days if they've got a cold one day and they haven't, and then they're feeling great another. So just to give you that idea, I've got a little picture of an orthographic recorder, a chart recorder down the bottom, and this is where a lot of our ideas are originated with that sort of data. So we're taking the example of the graph at the top here. This comes from an ASTM standard, and it's talking about identifying an initiation point with a crack from a voltage signal. So you're told to find this linear fit. You're told that this is a linear region, so do a fit line to it. Okay, great. Well, okay, I'm going to put my ruler against it and say, oh, it's linear between about there and there. And where does it come off the line? Well, okay, it's there. And actually, where there is partly my interpretation, and partly it's going to be influenced by how wide the pencil line was or the pen line was. Now, with modern data systems, we get pros and cons to this. And generally, I would say that they do help, but you have to use them appropriately. So it's great. We have higher resolution. We know exactly where that line is, or where each data point we've recorded on it is. We're not bound by the width of the line, the width of the pen nib on the chart recorder. We can get huge amounts of data, and it can be any size we want. So we can look at it on any scale we want. Trouble is that for humans, it can be too much data. And you get into questions of, well, I look at it at this scale, and well, there's the end of the linear region. And then you zoom in a bit, and you start thinking, oh, well, maybe is that the linear region? How linear is linear? In question for the ages. If we talk about that raw data that we collect, then there's sort of a mushy zone between quality and quantity, and sometimes our nice modern data systems give us an advantage just by sheer quantity. So when we've got a small number of data points, then each one, the uncertainty on each one can become significant. So this is a very arbitrary example, but let's say that those I've collected only 3 data points, but they're all actually within the scatter of my measurement, the uncertainty of my measurement. So if I collect 3 data points and I just take the average, I could randomly end up within the scatter from the same measurement, the uncertainty from the same measurement. I could infer a different average, and it's utter nonsense. This is a very simple example of trying to get the idea across, but it becomes more and more complex when we start talking about continuous data, or when we've got a population of dozens or hundreds or thousands of data points that we need to fit. And that's where you start getting safety in numbers, where fitting something that's constant, but you can see the scatter and understand it, has its advantages. So you can use a lot more readings and smooth the noise to reduce the uncertainty. Now there are all sorts of techniques which help, and they can be signal conditioning filters. I'm sure some of our other presentations will talk a lot more about that. Or they could be data smoothing or averaging approaches once we've recorded it. But they must be used with care. So just to illustrate that point, let's talk about a fatigue test where we were driving a very slow test with a triangle wave. So let's say our intention is the black line on this graph. And the yellow line is what we actually record, or the raw data. Okay, very well. Now, there are several things that could happen here. If we don't collect enough data, so if we just let's say we were taking rather infrequent readings and we only got those points circled in red. Now look, we don't actually have one that's on the point of the triangle. We've missed the peak. Excuse me, interference from my computer. There we go. Then, if we filter it and we're really smoothing lots of stuff out, we get the green line, but we've rounded the point off. Now we've clipped the peak value, so we're under reading again. But if we don't filter very much, and we take basically the raw data, and then we've got a bigger influence from our noise. And so are we under-reading? Are we over-reading? Or do we just bind that uncertainty into our measurement, into what we declare? So skipping quickly on, and please do ask me to go back to this at the end if you want to discuss more, because I know I'm starting to go quite quickly. Let's think about the other side of what I've been talking about, of fracture toughness. And let's look at a supposedly simple critical fracture toughness. So you've got a crack, you pull it, and there's a critical point at which it breaks. There's a very well-defined methodology for this. So yeah, it goes snap. Okay, fine. There's a definition of this using find the linear slope. put in a second, and that's your point. Now, but the trouble is, fitting the slope affects where you find the critical point. So a little over 10 years, bit over 10 years ago now, the first attempt at this was done, the first assessment on this was done by Mark James and Pete McKeegan, and done for ASTM, and they looked at finding the toughness value and getting about 12 different labs to evaluate. And you can see that this is the coefficient of variation for just what that critical point was, what the value was. And sometimes it is wildly varying, but on other data sets, it's pretty close. So, and this is purely defined and purely driven by the analysis. Now, more recently, I've got involved with helping sort of a second bite at this, because since then there's been a standard developed for specifically to repeatably find the linear section of a test graph, a test record. So let's look at we took actually some of the same data and got a series of labs to do their evaluation. And you look at the variation from the average result, and some of them are not too bad, and some of them are getting bigger and bigger variations. Now, if we compare those where it was using human assessment with where they'd implemented the computer-based algorithm, so look, I mean, I think that graph tells you a pretty strong tells you something pretty strongly, that mostly there is zero variation anymore, and when there is variation, it's less than a tenth as much as you were getting with the human in the loop. So briefly, coming around to the end here, I said I'd talk about uncertainty budgets. So this is where we sum up all the sources of error in the measurement system and say, well, actually, all in all, we know that our system, with every possible bit of randomness or error in our system, it must be within this much of the true value. And so that's not bad for a single static parameter like applied static force, let's say. Seems all good. If we're finding a single point from a two-parameter array, so let's take the example of just finding the ultimate tensile strength, which is going to be the peak force if we just slowly stretch our specimen and until it goes snap. So we can express that as a two-parameter array of force versus displacement, stress versus strain, I should say, or even stress versus time. Just find the maximum. You do need to start considering those data recording effects, which I was talking about, and you might need to consider the search algorithm that's finding where the highest one is. But again, it's not looking too bad. So your budget is getting a bit bigger, but having a few more lines in it, but it shouldn't be too bad. Now, once we start to get into things which are also sometimes seem simple, like modulus of a material, the Young's modulus, we're actually quantifying shape of an array. And identifying the region and fitting becomes really quite important. It will significantly affect the value. And how you start quantifying that is hard. If we take it to the final stage, then we start saying durability tests, let's say a fatigue test, and you've got many parameters which can affect the result, and not all in the same way. Now, this isn't something that's widely discussed beyond the, well, we ought to think about it, but we don't quite know how to do it, is the most common discussion. But it's not impossible. And just to sort of to discuss that point very briefly, uncertainty for an individual fatigue test, one specimen. It is possible It might not be easy. Also, the question to which I personally don't know the answer, some of the rest of the community and within EIS might have a better answer for it, might have good ways to explain this, is it useful? What do you do with that uncertainty? So is it possible? Yes, but surely scatter is expected, just from the defect in each specimen. True, but also, once we've done a test program, or some past ones, we've got a good assessment of how different parameters affect the average result. So temperature versus fatigue life, strain amplitude versus fatigue life. So for each of our parameters, let's say the strain amplitude, we can evaluate an uncertainty. And because we know about the test program as a whole, we can derive that theoretical contribution to the result uncertainty. And we can collect those together. That means that we actually know if you retested the same specimen in a parallel universe, so it's got all the same defects, all the same problems, but the randomness in the test system means you know that there must be some variability. Now we're in search of truth and beauty at this point, and sort of it's all getting a bit metaphysical. But you could say that this is the fatigue life, and it's got none of this specimen, and it had an uncertainty of this number of cycles, which is quite a bizarre idea in some ways. But there's some amazing work done on this back around the year 2000. The UNCERT project, which was done by NPL. And led by Fatih Kandil, who it's I honour to know reasonably well. You can go and look at all the reports from this. They're hosted on the NPL website, and I'd encourage you to do so if you're interested. Final slide. So I've talked about all these things about uncertainty and all these problems, and whether you actually budget them or whether you try to eliminate them as best you can and deal with the output. Why should we care? And the fundamental thing is that reducing uncertainty in this sort of tests, in durability tests, whether they're about fracture mechanics or whether they're about fatigue life, it gives us better design allowables. So you look at the little graph here, and we've got a fatigue life, an SN curve, well, an EN curve because it's strain range, and you can see the scatter. Now, what we have to do when someone is designing an aircraft structure or something, they have to take a 95-99 confidence limit, which is the green line here. Apologies if that isn't very clear on screen. And that's actually quite well to the left or if you prefer, quite well down from the average curve. So if we get rid of the uncertainty, then we will reduce the scatter. And if we reduce the scatter, then we can pull up our confidence line. That gives us better design allowables, and it means, and it's going to cost us with more careful setup. It's going to cost us with more codified analyses, but the benefits are that we are safer. If we're talking structural design for be it medical devices or aircraft, and they're more efficient. And so, you know, it is that thing of, if we talk about that hot fatigue, high temperature, low cycle fatigue, we can run a few degrees hotter in the engine. We get percentage, you know, a few percent or even points of a percent better efficiency, better for the environment, better for everyone's pocket. So it's all about giving us better design at the end of the day. So I'm going to wrap up there and invite people to ask questions if you so desire. Hopefully Sarah and Dave have been keeping an eye if you've been putting stuff in the chat. So feel free to raise your hand, put a question in the chat, just crack your microphone and shout out. And I hope that's been interesting if you don't have any questions.
Thanks very much, Peter.
I think we have a question from Raoul.
Yes. Hi, good afternoon. Hi, good afternoon, Peter. So in
Hello.
the hello, in the slide previous to last, if you could show it again, if you
Yes,
don't mind.
I'll put that back on screen.
Thank you very much.
So yes, there we go. So we've got our EM curve there.
Yeah.
Sure.
Sorry, the previous one to this one. Sorry.
That one. Yeah.
Yeah. So I feel very curious about this paragraph in the middle. With knowledge of a test program, we get a good assessment of how different parameters affect the average. So can you? I kind of understand what you're trying to explain there.
That's absolutely fine. But let me unpack that a little bit.
Yes.
It's a really great question because I did flash through it. I'm going to give you the brief version of this as best as I can, but definitely read the report if you're interested. What happens is we have, let's say we can say there's an uncertainty on what the strain amplitude was, and we have our strain life curve. So we know how, let's say 2%, a change of 0.1% in the strain amplitude will give you a change of life of this amount. We've got an uncertainty in the temperature, and we can correlate, well, for each 100 degrees in temperature, we get a shift in the life by this amount. So can you see what I'm trying to say?
Yes.
Okay, so you add those up, just like when we said about the uncertainty in one single measurement, that you've got the contribution from electronic noise and from mechanical vibration, and you're doing a similar thing, but adding it up on the effect on cycles to failure.
Okay. Thank you very much.
You're very welcome.
Okay, are there any other questions? Say thanks, Peter.
You're very welcome. I've clearly baffled people or hopefully educated them.
I was interested in an earlier part of there, actually, where you were looking at the overshoot of the test specimen affecting the result.
Yes.
It's also a thing that I'm very interested in terms of block program testing in some things, is where the order that you do the high loads versus low loads and so on during the block program test. It can make it's to the theory, it makes no difference if you do all of the big blocks first and then the small ones later, or if you do all the small ones first and all the big ones later on. But it makes a big difference to the material.
It does, and it's, I know enough to be very, very careful about that, because I've read some bits and I recognise how much how sensitive it can be. The one comment I would make there is from the materials testing viewpoint, and I know you're coming more from the structures and vehicles side, but from the materials testing viewpoint, there's some interesting stuff, and some standards moving towards standardization on tests where actually it's not a constant amplitude, but it's and neither is it random, not spectrum loading. It's constantly varying, so you're windowing, enveloping up, so cycle by cycle going up in a triangular increasing and then back down, and you keep doing this so that, and you build up a picture of how that changes during the life of the specimen. I don't claim to fully understand how they're analysing the output of that, but there's some great stuff from it's one of the German universities who are working on it, and German automotive steels industry for automotive are very interested, and also If you've ever encountered Dr. Sunder, who does a lot of variable amplitude stuff over many years, he's been publishing some work recently from more of the aerospace alloys side of things.
Okay. I don't see any more questions. No, I think we can probably start to round off a little bit there, and maybe there will be more questions later on. Thanks.
Yes, absolutely. So feel free to email in, and questions will end up in my direction, or indeed the other presenters during these couple of weeks.
Okay. Do you want to round off, Sarah?
Yes, just to let you know that we have got some other events coming up, as Dave and Peter have alluded to. I'll just take you back to the ones we've got. I think 2 or 3 webinars next week in our Reducing Doubt in Measurement, Engineering Measurement and Analysis series. And we are, of course, always keen to welcome your ideas of possible future events. So do let us know of anything that particularly interests you that we think we should be turning our attention to. So thank you for joining us.
Just a quick add-on there, actually, the next one on Monday is mine, so it's going to be very, very interesting.
See, Dave is on that side of me, on my screen, possibly not on yours.
Thanks very much, everybody.